Hello and welcome to today's lecture. Today we will look into the concept of dimension and finally define what it means for an affine variety to be of a certain dimension n. So our goal is to extend the notion of dimension as we know it from that of vector spaces into the world of affine varieties in a way that agrees with our intuition. So that, for example, what we think of as curves or surfaces has dimension 1, 2. Before we go about doing this, one might think, how do we actually define the dimension of a vector space? Well, usually this is done by constructing bases and then saying that the dimension is the number of vectors in a basis. The problem is that, of course, our objects are not linear. We don't have any notion of the basis. So one way to think about the dimension of a vector space is as follows. So let us work over the real numbers. If we want the dimension of R3, that's of course supposed to be 3. And so we have this three-dimensional space. But what does it finally mean? Well, one way to see it is the following. The smallest possible subspace in R3 is the zero subspace. That is the point. The point sits inside the subspaces of the next dimension, namely lines. So the smallest subspace that properly contains the origin is a line. And the smallest subspace that properly contains the line is a plane. And the smallest subspace that properly contains such a plane is all of R3. So the statement that R3 is three-dimensional somehow philosophically depends on the fact that the longest possible chain of subspaces ordered by strict inclusion has length 3. The point is included into a line, into a plane, into the space. This is the idea we will build on. And we will study dimension globally and also locally by defining what it means that something has codimension n. Also, we will express dimension algebraically to as always, view our objects from two sides, one algebraic side as rings and one geometric side as affine varieties. So let us go into the definition. So we start with any Noetherian topological space X. We define the dimension of X to be the supremum of the lengths of the chains of non-empty, irreducible, closed subspaces of X. Subspaces, of course, in the sense of topological subspaces. So such a chain starts with x0 and goes on up to xn with strict inclusions, and the supremum over all n for which this is possible is the dimension of X. This is exactly analogous to the example of vector spaces that we just saw. Also, given an irreducible subspace that is not empty and that sits inside X, we define the codimension of Y in X, denoted in this way, to be, so to speak, the part of the dimension that remains from Y up to X. So it is the supremum of the lengths of all chains of irreducible closed subspaces that contain Y. Let's look at examples. If we have a space with one point, then the dimension is 0. This is because in such a chain as we discussed of non-empty, irreducible, closed subspaces, we have to start with x0 being the point, and there is no way to extend this further without exiting the space, so the point has dimension 0. Let's look now at the line with the Zariski topology. So we're looking at the line A1K with the Zariski topology. So pause and think what you think the dimension should be. Well, the smallest possible size of a subspace is a subspace of 1 point. So I can have x naught to be 1 point. And then the smallest irreducible subspace of the line containing a point properly is the line itself. So the dimension of A1 is 1. Let us now look at the following affine variety, again with respect to the Zariski topology. So it is the union of the x1, x2 plane and the x3 line. What is the dimension of this space? Well, we need to calculate the supremum of the lengths of chains of inclusions of irreducible subspaces. So maybe I start with x0 to be this point. And as my x1, I take the line. Because there is no intermediate irreducible set between the point and the line. So I get a chain like that I cannot extend further because x1 doesn't sit inside any irreducible subspace of this space. This space is reducible. It is the union of two closed sets. So this was one chain. If instead I had started with a point here in the plane, then any line containing it is irreducible. So maybe this is my x1 prime. And then I can take the plane to be my x2 prime. So now I have x0 prime sitting inside x1 prime sitting inside x2 prime. And if you try, you can check that you cannot choose any bigger chain, you cannot choose any longer chain, and therefore this shows that the dimension of x equals 2. But we also make an interesting observation. These points aren't created equal. The codimension in x of the point x0, so since x0 denotes the set of the point, I can write it like this. This is 1. This is a point of codimension 1 in the variety. Pause and go back to the definition and convince yourself why this is true. Whereas this other point, x0 prime, has codimension 2. This is, of course, some lack of homogeneity that doesn't happen in vector spaces. So when this doesn't happen, so the problem here was that different irreducible components somehow had different dimensions. And so we call a Noetherian topological space a space of pure dimension n if each irreducible component has the same dimension n. And if we're talking about an affine variety, then if it has pure dimension 1, we call it a curve. If it has pure dimension 2, we call it a surface. If it has pure dimension m-1, viewed as a subvariety of an affine variety of pure dimension m, then we say it is a hypersurface. So we lose one dimension there. And one remark is that there does exist an infinite dimensional Noetherian topological space. That can happen. But as we will see, all affine varieties will be infinite. It will be finite dimensional. But this is something that needs to be shown. But just Noetherianity by itself does not prevent infinite dimension. Let's now look at an algebraic view of this. So all of this is perhaps easy to see what is going on, but at the same time, it seems that we need a more rigorous apparatus than just picking points and drawing lines to determine the dimension of a variety. So let's put varieties and topological spaces aside and consider rings. We want to define the dimension of a ring. So the dimension, or more precisely the Krull dimension of a ring R, is the supremum of the lengths of all chains of prime ideals in R. This is a reasonable thing because remember, in the back of our head, we have R as being the coordinate ring of an affine variety. And in that case, prime ideals correspond to irreducible subvarieties. So this is somehow similar to that definition. And we can also define the codimension of a prime ideal, or sometimes called the height of that prime ideal, to be the supremum of all n, with chains of prime ideals contained inside P. So you might have expected P to be contained inside this chain, but remember, we are now looking at rings, so all inclusions are reversed in the sense that the inclusions that we want to hold for irreducible subvarieties will hold inversely for prime ideals. So this is, as we will see, the proper definition of the codimension of a prime ideal. Let's look at some examples. Fields have dimension 0. Yeah, simply because there are no prime ideals except the 0 ideals, so any such chain will start and end with the 0 ideal. Other principal ideal domains, meaning principal ideal domains that are not fields, have dimension 1. Why is that? That is because, as we know from algebra, in a principal ideal domain, an ideal is prime if and only if it is maximal for non-zero ideals. So this means that we have the 0 ideal that will sit inside some maximal ideal M, and that's it, and therefore the principal ideal domain will have dimension 1 if it is not a field. So now we have defined the algebraic dimension of a ring and the geometric dimension of an Noetherian topological space. It would be sad if, when taking the special case of the coordinate ring of an affine variety, these two notions would give different numbers. Thankfully, this is not the case. So the proposition is as follows. If you have an affine variety X, then the dimension of X as a Noetherian topological space is equal to the dimension of the coordinate ring of X, the Krull dimension of the coordinate ring of X. And if you have an irreducible subvariety Y that is not empty, then the codimension of Y as a subspace equals the codimension of the vanishing ideal of Y as a prime ideal in the ring, or if you wish, the height of I of Y. And notice that since Y is irreducible, I of Y is a prime ideal. The reason for this is this bijection between prime ideals and irreducible subspaces. There we have this one-to-one correspondence that reverses inclusions. So in particular, it doesn't change the lengths of chains of prime ideals or irreducible subspaces. So therefore, the dimension as defined in terms of irreducible subspaces is the same as the dimension as defined in terms of prime ideals. And prime ideals contained inside I of Y correspond to irreducible subspaces containing Y. Again, because of the inclusion reversing business, which means that the statement about the codimension holds as well. So now we have these two notions of dimension, and we can work with them to prove some interesting properties of affine varieties.